Hello everyone, let's talk about the intermolecular forces. So your intermolecular forces are the attractions between the molecules. For example, if I take two molecules of HCl, which is hydrogen chloride, then the way those two molecules will be attracted to each other, as you see in this picture, is what we call the intermolecular forces. Comparatively, what we learned earlier about the bonding, where let's say here we're just looking at one HCl molecule, the way hydrogen and chlorine are attached to each other, that's a bond right there. So that is an intramolecular force because those attractions are within the same molecule. So that's the difference between bonds and intermolecular forces. Please remember that intermolecular forces are not bonds. So you guys need to know about three types of intermolecular forces for the regions. And the type of those intermolecular forces and their strength, some of them are weaker, some of them are stronger, that depends on the polarity of the molecule. So once again, that's a quick review from the bonding unit. Remember how we were talking about the polarity of the bonds, and then we were talking about the polarity of the entire molecule, where we use the snap rule. If it's symmetric, it's nonpolar. If it's asymmetric, it's polar. So the first type of intermolecular force is for the nonpolar molecules, and nonpolar molecules have London dispersion or van der Waals forces. So here we are looking at two molecules of carbon dioxide. Carbon dioxide is nonpolar because it's a symmetric molecule. So the way two carbon dioxide molecules are going to be attracted to each other, as we see in this picture, those attractions will be the van der Waals or London dispersion forces. And these are actually the weakest out of all the intermolecular forces. And then for the polar molecules, they can either have dipole-dipole attractions, and these attractions occur between two different dipoles of two molecules. So in this case, when we are looking at two molecules of hydrogen chloride, the partial negatively charged chlorine of one molecule is attracting the partial positively charged hydrogen of the other molecule. So again, the partial positive and partial negative are going to attract each other, but not on the same molecule. The partial negative of one molecule attracts the partial positive of the other molecule. So remember how we said that these partial positive and partial negative parts, they are the dipoles, and that's exactly why the name of this type of force is dipole-dipole attraction. And because this is between polar molecules, it's actually stronger compared to the London dispersion forces. Another type of intermolecular force for polar molecules that we need to know is hydrogen bonding. And hydrogen bonding occurs between polar molecules that have a very high electronegativity difference. And also, very specifically, hydrogen bonding only exists in molecules that have either a hydrogen bonded with fluorine or oxygen or nitrogen. If we do not see a polar molecule that has any of those three bonds, then that molecule, when it comes in contact with another molecule, a polar molecule, it's just going to have dipole-dipole attractions. But if we have a molecule that has any of these three bonds, when it comes into contact with another molecule like itself, it can have hydrogen bonding. So here's an example of the water molecule, because water does have a bond between hydrogen and oxygen. So when one water molecule attracts another water molecule, again, the partial negative and partial positively charged dipoles are on the different molecules are attracting each other. But because we see that bond between hydrogen and oxygen, this molecule actually also has hydrogen bonding on top of dipole-dipole. So it can have two different types of attractions, but because hydrogen bonding is stronger compared to the other two, so your first answer should be hydrogen bonding if asked that what type of intermolecular force this thing is going to have. So now that we know the three different intermolecular forces, the next thing that we talked about was how can we use that information to determine the phase of any given matter. Ideally, if we are asked to determine the phase of an element at any specific temperature, let's say we're talking about room temperature, which is 298 Kelvin or 25 degrees Celsius, we just go to table S and we compare that 298 Kelvin with the given melting point and boiling point of that substance. So if your given temperature, which in this case is the room temperature, if it's less than the melting point, that means this thing has still not started melting, so it's still in the solid phase. If your given temperature is between the melting point and boiling point, that means this thing has already melted, but it has not boiled yet. So it's in the liquid phase. And if the given temperature is greater than both the melting and the boiling point, that means this thing has already melted and already boiled, so now it's in the gas phase. The problem is, table S does not give us any information about the compounds. So in case of compounds, we actually look at the intermolecular forces. So we look at the structure of the molecule, and depending on whether it's polar or non-polar, we figure out whether what type of intermolecular force this thing is going to have. We know that the piece of information that we need to remember is that solids have the strongest intermolecular forces and gases have the weakest intermolecular forces. So the two molecules that we looked at in the class, and this is just a screenshot from my key of the notes, not super pretty, but we can still talk about it. So we looked at carbon dioxide, which is a non-polar molecule, and hydrochloric acid, which is a polar molecule. So the type of intermolecular force that we'll have between two carbon dioxide molecules would be linear dispersion, which is a weaker force compared to dipole-dipole forces, which we will have in two HCl molecules, which is exactly why carbon dioxide occurs as a gas at room temperature, and hydrochloric acid is a liquid at room temperature. And we also did a little bit of practice with table S by looking at fluorine, bromine, and iodine. So if you just look at the melting point and boiling point of these three elements in table S and compare that to room temperature, 298 Kelvin, fluorine turns out to be a gas, bromine is a liquid, and iodine is a solid. So another piece of information that we were able to get from the same compounds is, notice how as we are going from fluorine to bromine to iodine, the gram formula mass is increasing. So what happens is that the higher your gram formula mass is, the stronger the intermolecular forces are going to be. And we know that because fluorine has a lower gram formula mass, and it's also in the gas phase. And remember, gases have weaker intermolecular forces compared to iodine, which has a higher gram formula mass and it occurs as a solid at room temperature, and solids have stronger intermolecular forces. And then finally, we connected the intermolecular forces with the boiling points of substances. So we looked at 4 different compounds and we made their Lewis diagrams. We tried to determine whether they're polar or non-polar, depending on if they are symmetric or asymmetric. And then we determined the type of intermolecular force that they are going to have. So CCl4, because it's non-polar, would have linear dispersion. HBr would have dipole-dipole. It's polar, but it has no bond between hydrogen and oxygen, fluorine or nitrogen. CH3OH does have a bond between hydrogen and oxygen, and it's also polar, so that's going to have hydrogen bonding. And then CH4 is also nonpolar, so London dispersion. And then we had to rank these 4 compounds based on which one is going to have the highest boiling point and which one is going to have the lowest boiling point. So remember that your boiling point is the temperature at which a substance starts boiling, which means it starts going from the liquid phase to the gas phase. So if something has very strong intermolecular forces, that means the particles are very strongly attracted to each other. So in order for that substance, the particles of that substance to go from the liquid phase to the gas phase, we need a lot more time, or those particles need a lot more time to break free of their intermolecular forces and actually convert to a gas. So that thing is going to start boiling at a higher temperature compared to something that does not have so much attractions between the particles. So the stronger the intermolecular forces are, the higher the boiling point of the substance is. So in this case, because CH3OH has the strongest intermolecular force, it's going to have the highest boiling point. And then comes HBr, which is dipole-dipole, or like the second strongest. And then out of CCl4 and CH4, both of them have London dispersion. But then CCl4 actually has a higher electronegativity difference, because remember, the strength of intermolecular forces overall depends on the polarity of the molecules and the bonds. All right, and that was pretty much it for the intermolecular forces.